Dr. Professor Satish Patil is at Indian Institute of Science, Bangalore. He's a very distinguished personality. He got his PhD from University of Wuppertal, Germany. His area of interest is organic solar cells, biodegradable polymers for drug delivery, polymer nanocomposites, etc. He has got 5 patents to his credit. He is having more than 100 publications, and he has an H index of 36. He is honored by a number of awards. To mention a few, he was given Swarna Jayanti Fellowship for the year 2013-14, and the Young Scientist Award, Young Affiliates of the World of Academic Sciences 2013, INSA Young Scientist Award in 2009, Young Associate of the Indian Academy of Sciences, Bangalore in 2009 to 12. He was awarded with Bronze Medal by Chemical Research Society and Material Research Society of India. He was given Professor Kaushal Kishore Memorial Award by Society of Polymer Science. He was also given Young Scientist Award in 2012 by A.V. Ramarao Research Foundation. He was also chosen as Outstanding Young Faculty Award by Microsoft Research MSR India. Today he is going to talk about exciting world of molecular electronics. I invite Professor Satish Patil to deliver his lecture. Please, Satish Patil, please.
Yeah, thank you, sir. Thank you very much. Very good afternoon to all of you from Bangalore. It's unfortunately it's a rainy day today here in Bangalore, but I don't know how is the weather over there. So let me just start sharing my slide first. I hope. Yeah. Okay. Can you see my slides?
Yes, but not full screen.
Okay, I'll just go for a full screen now. Yes, Pradeep?
Yes, good.
Okay, all right. Thank you. Okay. So thank you. Indeed, it's a great honor. I must thank Pradeep and the organizer for giving me this opportunity to share some of our ongoing research activity in the area of molecular electronics. I heard many good things about this meeting. This is a series of meetings, I think, every year. There are very scholarly people have presented. So I do consider personally this is a great honor for me to present my work in this meeting. So today I'll be talking about exciting world of molecular electronics. That's a very generic title I have given, but I will be a little bit touching upon how indeed molecular electronics made a difference in the energy sector. So specifically my focus would be in energy. I would be touching upon solar cells mainly, also a bit of a LED part for light emitting diodes. And then I'm considering the majority of the audience in this meeting are students. I have made it very, very sort of tuned my research topic towards the students more rather than, going for a very advanced research topic. So going forward, let's start. So this is world's first computer. You see that today, this computer was required a massive amount of space to store, required a tremendous amount of manpower to operate. And you see that these like for example, if you look at this, these processors are extremely tall. I think so you need a big auditorium to store the computer. So this is the way the computer journey began. And let's see what happens today. What is the computer today? Today's computers are tiny devices. They are very powerful, store tremendous amount of energy, and you can do many things today with computers. So today I'm sitting in a Bangalore by using a small device and I'm communicating to you, whereas the rest of the world we can communicate by using these small computers. So this is something that's very sort of a journey for a molecular, for a optoelectronic devices, where the things began with not very big way, because the devices were not made. Devices were initially not really run by by using a small amount of energy. But today's devices are very powerful, and you utilize small power and you use the similar story with the cell phone. You look at the cell phone here. This is Dr. Cooper speaking with his colleague in the next room. This is world's first cell phone, and he's delighted to speak with his colleague. They could communicate with each other from a small distance, across the room. And you see the cell phone weighs almost like 3.5 kilo. If you just Google it, this image, your cell phone weighs 3.5 kilogram. Today's cell phones are very tiny devices in terms of, you can carry them in the pocket, and they are also very, very sort of a very powerful devices. Majority of the things you can do on the cell phone, you can connect to friends, you can connect to do, many things. You can even to nowadays due to WhatsApp, you can always work on very, very powerful devices by using the cell phone. So essentially, you see that there is a tremendous amount of research has went in to change the way we are looking using the technology today. So there has been a miniaturization time to time from the devices. For example, the number of transistors used in the world's first computer are not on an integrated chip actually. So, but today we have millions of transistors were integrated on a chip, and this has been made a computer is a very, very powerful device. And some of the display are excellent. If you look at some of the display of the cell phone today, what we have, these displays are essentially done with basically fabricated with the molecules. Molecules indeed play a very, very important role here. I will explain a little bit about how molecules play the role. So eventually, I'm trying to impress upon you here is there is a miniaturization in the in a devices. We have energy saving devices today, but that is sufficient? Where we are heading, and why do we need to think about more about energy? How we are going to make a big impact in the energy research? So it's the same thing with the computer. Other than I gave two examples: computer and cell phone. It's the same thing with the television also. CRT, I don't know, many of the people in the audience, they have not even seen CRT, at least during my time, I have seen CRT. CRTs are cathode ray tube based televisions, are heavy, gigantic, need lot of power, and they have to really need one, even just shifting from one room to the other room, you need a manpower. But today's televisions are based on organic light emitting diodes, and they are also based on a LCD plasma based systems. They are foldable, they are very tiny devices, and they're aesthetically they look very elegant devices, and they consume very less power, and there is indeed evolution of a display technology. And nobody likes to have a sort of a very dim and fuzzy displays. Everybody likes to have a very colorful display. So you can see especially with this kind of a HD channels, you can really see a background images beautifully actually. So there is indeed evolutions in a television world as well. So this is something today, if you look at molecular electronics, indeed made a big impact in these devices. Molecular electronics so future world is, this is all majority of the, thanks to Google, these are the images where the future world is going to look like this. This is a building I have shown, BIPV, building integrated photovoltaics. This is a, if you look at these colorful, some of the building material, these colorful build part is basically a integrated photovoltaic devices has been integrated in the building to make these buildings self-sufficient, so they can produce the energy. So this is the way the future is going to look like that, but you have to really put an ink. You cannot put a solar cells here. So molecular electronics is going to make a big difference here. Similarly with the OLED is coming big way. Light emitting diodes have, it's $1 billion industry which is emerging very fast to replace the traditional lighting, whatever the way we light our houses today. So OLED is also coming a big way in this area. But there are still very basic fundamental questions one need to answer before we commercialize these technologies. So let's look at why do we care about essentially about the molecular electronics. So this is a questions which is bothering for the entire global community. We have to have a energy produced from the renewable sources. For example, if you look at the map here, this is a map in the night. It's a collage map. You as you know that everywhere it's not night at the same time, but it's a collage map. The lighting industry, lighting takes tremendous amount of energy. Out of this 14 terawatt energy challenges, lighting requires a tremendous amount of power to brighten the world in the night. You look at some of the part of the globe, indeed some of the part of the globe is very dark, and some of the part of the globe is very, very bright. If you take India specific example, within India, stick at today's count, now if you look at today's number here, close to 40 million people do not have access to the light. And light plays a very, very important role in day-to-day activities. If you have a bright day, if you have a bright light, it makes a difference in education. It makes a difference in the growth of a country. It makes a difference in many, many other things as well. So what I'm saying is basically, essentially, lighting requires a tremendous amount of energy, and we'll see how we are doing today. Actually, this is the lighting options we have. So thanks to Edison, incandescent lamp was, we use still today. I think if you look at the difference here, the numbers which I have shown here, for an incandescent lamp required, if you read the numbers at the bottom, if you're seeing my slide very clearly, 40 watt, 1000 hours. It depends upon how stable power supply you have. This 40 watt could be a few seconds, fraction of second, the soon after you put light, it just shuts off. So it is essentially depends upon these numbers are different, basically depends upon how stable power you have it. Now today we don't use incandescent lamp because this is the most insufficient way of producing energy. Incandescent lamp, if you ask a student in the audience, that the way they produce the light is you use this tungsten filament and you supply the power and you essentially heat up. So by heating, you are making something under vacuum, you are brightening the room. Whereas the fluorescent lamp work in the mechanism of the fluorescence, where you have this fluorescent, coating on this one, but they are, there's a major difference in terms of number of power, the amount of power required to turn on the light and the number of hours we use it. It's a 10 watt, 10,000 hours. If you go to LED, it's 1.5 watt. You again consume the less power and you brighten the world. The idea is essentially, how are we going to minimize the consumption of the electricity or consumption of the energy? However, you do not compromise on brightening the world. So this is the challenge. But today, if you look at the cost of each of these technology, LED bulb, if you are going and purchasing a LED bulb in the market, it costs you 300 to 400 rupees. Whereas the incandescent lamp will cost about 10 rupees. So the challenge for people in this area, so is you cannot deploy a LED light across the globe essentially unless you reach the cost of a incandescent lamp. So this is the major challenge. Of course, there is a tremendous amount of a growth and a development in a technology. However, is that technology can you deploy across the globe? Can you make a difference in the life of the people? Where I was talking about these 40 million people even do not have access to the light and basic light. How are we going to afford to provide them a LED light by which is so expensive? So the challenge is, how are you going to make it cost effective? Is molecular electronics going to help you to make these LEDs very, very cost effective? So today's these LEDs are built on a compound semiconductor like material like gallium nitride. So there are other very, very cost consumable materials have been used and people have made LED. So the question is, can you really make LED a cost effective LED by using a molecules? So this is we take a motivation from this, and everybody should take a motivation from this. You see that when Edison first shown his discovery, I have a light, people mocked on Edison's discovery. Edison's was the efficiency of a light present in lumens per watt. So he presented first light 1 lumens per watt is as good as candlelight. But he made a statement saying that I have not failed, but I have just found 10,000 ways that won't work. So he essentially looked at each and every element of the periodic table and see that whether he can make it a cost-effective light, okay, a cheaper light. And today we indeed use Edison's discovery for this one. So a little bit now technical, okay, going forward, how you generate the light. Let's think about, there are two aspects of generating light. This is a very basic Jablonski diagram of a photophysics. You must be learning this photophysics diagram in your part of your undergraduate syllabus in your college. Here is the way you generate the light. So if you shine the light on a, basically on any molecules, the incoming light energy, when it meets to band gap of this material, then you excite the electron in the photoexcitation. And that electron, when it meets the hole, essentially in the ground state, we have many losses there. I will not go that part very detailed because it requires a couple of lectures to talk about that. So, but what happens is there is an internal conversion here, and you have a light with the fluorescence form. There is also a competitive pathways for this excited state electron. You have intersystem crossing, the electron goes to the triplet state, and the triplet state is a spin forbidden, and you see a very delayed phosphorescence. That's not really a contribute to the quantum gate. So this is the photoluminescence, and when you do electroluminescence, that's the way we generate light. If you look at our light, we are brightened today, your room is based on electrical excitation. So electrical excitation is you supply the power. When you bias the device, you inject a hole and electron here. When you inject a hole and electron, essentially this hole and electron have a sort of a opposite charges, because one is electron. And can you please mute? Hello? Somebody is not muted. Sorry. Yeah, okay, all right. So going forward, basically here in this case, you see that a hole and electron is excited. Okay, you excite, you inject by having two different electrodes, you inject a hole and electron, and this hole and electron meet, and you have essentially emit the light of the band gap energy. But there are issues and problems here, which I will tell you how we cannot make it a bright LED by using molecules. So this is the device architecture. A student of physics in the audience or people who have physics background, they would know that. What is this one? You have sandwich structure of a cathode and anode. Here, two electrodes has been sandwiched. And if you, how we are going to, this EML is a emissive layer. So this is the emitting material. Today's LEDs emitting materials are indeed fabricated with a very pure material of a, like for example, gallium nitride. It's a multi-layer devices. So they will be grown by CVD, and these are all inorganic compound semiconductor. But the challenge is, if you make something out of solution, if you simply coat this ITO layer out of a solution, can you really make it a cost-effective LED? And of course, there are HTL, ETL, hole transporting layer and electron transporting layer. I will not dwell very deep into the physics of how these HTL and ETL layers are. Let's have, going forward, just try to understand. The thing is, basically you have two electrodes and you have emissive layer, and you are applying the bias and you are getting light out of it. How are you going to make it a light which is more efficient? So this is multi-layer. I will not spend much of a time of doing a multi-layer here, but you have to really build these devices, fabrications. But for the sake of understanding, you simply look at the left panel of my device, where we have an emissive layer, and we have sandwiched this emissive layer in a two unsymmetrical, two electrode which have a different work functions. It's an unsymmetry there. And essentially you make a diode and you apply the bias and you get the light. So then there are efforts across the globe. Actually, people have, and I know, recognize the importance of a molecular electronics. They started developing materials. For example, simple material like anthracene, coumarine, xanthine. These are all make it in kilogram scales. In the laboratory scale, you can really make it in a large scale. And they are really make it with just a few steps in chemical synthesis. Actually, today's world, if you look at now, you can make it like a combinatorial synthesis, you can make it many things, and you can make it these things very cheap. However, at the parallelly, a polymer chemist also made a pi conjugated systems, and they are also indeed fluorescent. Actually, so polymer chemistry evolved parallelly, because there is a difference between small molecule and polymer. When you make a small molecule, you have to really ensure that you thermally evaporate and prepare a thin film. The thin film I was talking in the previous slide, where we have a thin film between the two electrodes. When you make things from the polymer, it is easy to cast a thin film from solution. So that's a difference between small molecule and polymer. So polymers are solution processable, whereas the small molecules, you have to really fabricate the thin film by using thermal evaporation. So that is not really a cost-effective method. In other advantage with the polymer is you can also print these polymers on a very flexible substrate. You can make an ink out of it, and you can make it a LED out of it. So this did not really work very well. I will explain you why this did not work very well. So there are issues here. So this is a bit of I will spend some time on this slide where I will talk about where is the fundamental challenges area where people have not really solved the problems. So you have hole and electron. These are two spin half particles. and they combine and meet in the emissive layer. Okay, remember that in a previous slide I have shown that you apply the voltage, you inject hole, which is a spin half particle, and you have inject the electron, it's another spin half particle. You have absolutely no control over the orientation of a spin. When they meet together in emissive layer, there is a possibility of these spins, how they rearrange themselves. So if you simply take a wave function of a spin half particle and wave function of a spin other particle, and you see that how the possibility of how they combine and produce a sort of a exciton here. Exciton is a neutral particle. When these two guys, a charged particle come together. What essentially happens here is a possibility of generating exciton is you generate a 25% singlet state where you see that total spin is 0 here with a 0 angular momentum, whereas you also produce 75% of a triplet here. So this is the mathematical ratio where you produce a very few singlet and very large number of it. It's a 1:3 ratio. And then as I talked about in the beginning of the Jablonski diagram, where triplets are, I said, spin forbidden transitions. So, okay, so just simply a selection rule, the triplets are not that emissive. It's a dark state. So what it matters for LED is a singlet state, which is a bright state. The question is, how are we going to harvest these dark states and improve the total quantum yield and make a best LED out of it? So these are the challenging in this area. So this is the reason if first generations, what I've talked about, they could only do a singlet state based LEDs. So then you do simple calculations. Again, this is, I will not dive very deep and not bore you, but one can look at how much a light out of you get from the singlet state. You can make it a 5% fluorescent material and 25% phosphorescent material. So to address this question, so the LEDs which was made for the first generations were certainly, there is a massive amount of a loss mechanism because all the triplets were not been collected. Essentially your total quantum yield is here is 5% out of the fluorescent material. To address that question, here is the one, again, historically, this is a Stephen Forrest and Mark Thompson's at University of Southern California here in Princeton. They combined it together. They came up with the idea of, can you use this hybrid material, where essentially organic, inorganic material. The idea they introduced here, which was very known in the literature, is called spin orbit coupling, where you can use a material like platinum and ruthenium, and then there is a indeed spin orbit coupling in those material and make triplet emissive. But turns out to be that this also turns out to be very expensive because ruthenium is these metals are very rare. In addition to that, there is problem with the how you process these materials. So that really did not work out very well in the favor of the LEDs. So today's LEDs, where my research group at IISc Bangalore is looking at a few aspects of this thermally activated direct fluorescence. So this is a person in it's a very recent idea of in around 2012, where Adachi in Japan, we came up with the idea of saying that, okay, can we make this singlet triplet gap so small? Actually, if you understand a exchange energy between S1 and T1, if you make it so small, you bring it to room temperature. So triplet, what you generate, you collect it back at room temperature purely by using a small molecule. So this is a metal-free organic molecules where they can be triplet harvested. So you are harvesting those dark states and you are making a efficient LED out of these material. So then, okay, then it's essentially, basically, if you look at in our group, what we try to do is we try to make it one of the light. One of the light, in a sense, when I say one of the light, we are trying to essentially make a blue light out of it. Blue light is very, very important component of a white light. How are we going to achieve the blue light? There are challenges in a blue light. So we set up this problem, similar like Adachi, can you make use of these dark states? So for a blue light, if you look at the blue light, you need a wide bandgap semiconductor. The wavelength for the blue light is in the range of 400 to 500 nanometer. In that region, you need a wide bandgap semiconductor. This is the first challenge. When you're designing a material in the lab, one has to understand what wavelength the chromophore emits the light. The chromophore emits the light in the blue part of the spectrum, means you need a band gap of the material is 2.9 to 3.1 eV. This is the reason you see that gallium nitride is a blue light emitting material. So similarly, you have to now think about what are the electrodes you are going to use it, what are the possible cathode and anode you have to use it, and accordingly you have to match your energy levels. Okay, so this is something which is you need to set it up problem properly, saying that what are the HTL and ETL, whole transporting layer, electron transporting layer, and how are we going to do it. So we started working on a very organic core, which is called basically these all rigid organic molecules. The previous speaker was talking about the use for the perylene based systems for the battery as a electrode material in battery. Here we thought of these rigid core materials have very little flexibility. If you look at the chemical bond between these binaphthalene rings, it's extremely rigid here. You freeze the rotation between these two binaphthalene. As a result, they become wide bandgap semiconductor and they emits in the blue part of the spectrum. And but there are issues. Again, it's nothing is easy. No, life is not easy here. If you try to address these questions, and you have to be really, other problems will come, because these are all aromatic system. They aggregate in a solid state. So we use fluorine, and then when you started using fluorine underforms a fluorinone while alkylating those chains. So the chemistry becomes very, very challenging here. Once we have such fluorinone defects, then essentially the material becomes soluble, whereas issues is it becomes a defective class of material. So keto defect gives a green emission. So we came up with material like something called fluoranthene. This is the material we have been currently working. So this is the chemistry we did. I'm not going to show a detailed synthesis how we develop these materials, but however, the idea here is basically you make wide bandgap semiconductor and see whether we can harvest those triplets and can you make a blue light out of it. So that was the questions when I asked a couple of years ago a student of mine who started looking at, and we have to keep it chemistry simple. If you are a synthetic chemist here, so this is the interdisciplinary field of research. Remember that it is important for you to understand the optical properties of these chromophores. It is important for you to need to understand the basic synthetic chemistry as well. So you have to really connect these things from one to other, where what happened is basically you do simple Diels-Alder reactions and you produce these materials in a large quantity. So that's the idea basically. So we went ahead again because due to lack of time, you see that where is the emission now. We go and do a detailed study in optical properties of these chromophores. They indeed, the maxima of these peak is fluorescence properties in emission is indeed in the blue part of the spectrum, but the tail is popping up in the green part of the spectrum, which is a color impurity in a material. We have to really make sure that at least the maxima is in the blue part of the spectrum. We did a detailed study, we will not dwell very deep upon it, and build a device and then look at, are we really getting a blue color or not? We got indeed the turn on the, but if you look at our external quantum efficiency in the table, what you have done is indeed a very, very low EQE. We get blue color in a photoluminescence. So don't get completely deceived by the idea of seeing blue color, you got a blue color. You have to make a device and you have to really look at indeed is a blue color or not, but we were not been really successful in terms of achieving what we want, although we could make it wide bandgap semiconductor in the lab. So this is one aspect of our research. Now I will little bit talk about solar cells. Okay, so two topics I decided to discuss with you today. One is LED. I have impressed upon it why light is necessary and what are the aspects of the lighting. I hope I will have a time again. Pradeep, you warn me whenever I'm reaching out the time, please. Okay. So essentially, looking at basically how we're going to produce the energy. Look at the solar part of the aspect of this, by using molecular electronics. So today you see that how we the 14 terawatt challenge. How do you produce the energy? We produce the energy by using a nuclear some percentage, natural gas, and majority of the energy, the major fraction of the energy comes from the coal, which is almost like 50% of the energy. And this is something we, it has its own severe impact on the environment when you start burning fossil fuels. And this is where the renewable energy is very, very important, where you have to really replace, today's the way we produce the energy with the other means. For example, when I say other renewables, you have to think of solar, you have to think of nuclear, and you have to think of other ways. So today I'm going to discuss about solar energy, how to make a cost-effective solar cells. So this is the challenge. I think the previous speaker was talking about battery. Battery is you store the energy, whereas I will be stressed upon it. You can connect beautifully from the previous lecture to this lecture. So today I'm going to talk about how I'm going to really generate the energy. So light harvesting material, I have to use it to generate the energy. You supply to the, then finally you can directly supply to the grid, but it is good to have a battery because every 24 hours you don't get a sunlight. You get a sunlight, maximum sunlight in a daytime. You store that energy in a battery and it is good to supply to the grid. So the challenges are at multifold here. You generate energy, you interface with the battery, supply to the grid, and finally supply to the consumer. So this is all about a sort of a a heart of a energy research, where you have to produce a harvest sunlight and you have to store in the form of battery. So how people do it currently? It's a basically, people do it with very expensive way, where the essentially today's photovoltaic industry is dominated by silicon PV. Silicon is a choice of material, which I'll discuss a little bit why silicon is a preferred material than all other material. Silicon is a very available across the globe. It is not dominated in particular region of the world. It is basically the silicon physics is very, very well understood. People have not known about fundamental properties of the silicon. So there are many pros in favor of silicon, why people use silicon as a material. But then if you convert a raw sand of a silicon into a solar cells, it's a it's a sort of a energy conversive process. We have to really need a massive infrastructure to convert a raw silicon into a solar cells. So some of the few pictures I have shown, these essentially describe the steps. How do you get a device grade silicon? There are again multiple steps to reach to even the one which I've shown in a picture, and then you convert into ingot, slicing vapors, you fabricate the cell and model, and then photovoltaic system. So this is a way of doing a method of producing silicon solar cells today, but silicon has reached to its limit now. You see that we have to think beyond silicon because there are a number of reasons. First of all, it's an indirect band gap semiconductor. It's a lousy light harvesting material. It does not really harvest a good light. You cannot tune the band gap. It's a high temperature processing is indeed one of the problem with the silicon, because it is not really, you cannot process from the solution. I would be cautious to make a statement saying there's no further room for miniaturization, but it is very, very challenging miniaturize further. It's instead of saying no further room for the miniaturization. Whereas if you just compare this one with the molecular semiconductor, you can tune the band gap as depend upon the kind of applications you are looking. If you are looking at, as I shown in the first part of my talk, you can tune the band gap and you can make LED out of it. You can tune the band gap. You can make a narrow band gap semiconductor by changing the chemical functionality here. So you can engineer the functionality by introducing a various different kinds of a group, and you can make it soluble material. So they are all a solution processable. If you make a polymer out of it by putting such alkyl chain, those R chains, and then you can make it a ink out of it. Once you make an ink out of it, the processing is everything is at room temperature. You can print on a flexible surface. You can make it a very, very cost effective devices as compared to silicon. So this is the major advantage of having a molecular semiconductor to fabricate the optoelectronic devices as compared to the conventional semiconductor. Conventional semiconductor, like an example, is silicon, where the processing itself is everything is at high temperature. It's not cost effective. So that's the reason today we cannot deploy the solar cells across the globe. Although silicon is very mature technology, is a very rugged, it has a very, very high, long lifetime, like more than 20 years, good efficiency. It is almost very close to the thermodynamic limit. But however, when you're deploying this technology across the globe, you have many, many challenges. One of the challenges, how cost is the key here. They're not at all cost effective. So instead of silicon, the question is, can I use molecule? As I said, it's a low cost, lightweight, flexible. You can see, you can tune the physical and chemical properties, and you can make it a print out, a ink out of it. So the question is here is how you make it that way. Okay, you simply compare in the periodic table, silicon and carbon, they belongs to the same group, but they have a the properties as the carbon, can have a similar properties to silicon? Yes, you can really indeed make a silicon-like properties in the carbon, but however, you have to make sure that you have a conjugated molecule. It acts as a semiconducting material when the pi electrons are available to delocalize through the backbone. So this is very, very important aspect of making carbon behaving like a silicon in many aspects. So this is the pi conjugated system, and you can make it a device out of it. You can pack together. So solar cells I will give a bit of a historical perspective to motivate you what is the historical perspective for the solar cells and what is the current status of the solar cells. So the first Becquerel did the curiosity experiment in his just a simple in garage, where he in 1839 he did with the 2 platinum electrode he put in electrolyte solution and shined the light, and he observed the photocurrent. So nothing happened for almost a century, but people realized that there is the importance of a renewable energy. Around 1943, Chapin and Fuller used silicon. So that's where this was first demonstrated in Bell Laboratories in US, and that is the time this Silicon Valley, basically these all emerging optoelectronic devices were coming. Like people could put large number of transistors on a chip. There was a tremendous amount of activity were going on in how to miniaturize the silicon-based devices. So people knew a physics behind silicon very well. They created junction out of a silicon and made a solar cells out of it. They found a very decent efficiency. But look, there's the flip side, or the other disadvantage with the silicon is as I said, it's an indirect bandgap semiconductor. It's a very poor light harvester. You have to use very thick material. Okay, and that's the reason this technology becomes based on single crystalline. At least it is very, very not at all cost effective. Cost is one of the major bottleneck, and they are rigid panels. You have to heavy because the material is very. Those are the other disadvantage of the silicon solar cells, where you have if you put on the rooftop, it is not really lightweight material. So, and then it has, and it's a very rigid material, like a glass. So essentially, to address some of these questions with the silicon, second generation solar cells came in the picture, and then people did thin film solar cells. You see that now the material quantity becomes 2 to 10. The thickness of the layer is 2 to 10 micrometer thick, and the efficiencies are 10 to 14%. Whereas, but because soon after you convert from the single crystalline to amorphous silicon, the materials becomes a direct band gap, and you can harvest the more light. So, but they did not match in terms of lifetime, because there was an issue with something called Stabler-Wronski effect. If you keep on shining a light on amorphous silicon, the dangling bond between silicon and hydride get knocked out, and you have a poor lifetime in this one. So third generation solar cells, there's a flurry of activities. There are a lot of group working now to address some of the questions in the first and second generation. People use dye sensitized solar cells. Our group does polymer bit and perovskite little bit. We started very recently. I will be talking about mainly a little bit of a few slides I will present in the polymer solar cells. So this is a sort of a curiosity driven research. I would say it is not yet in a commercialized, because although perovskite is very close to knocking the door of the commercialization, but however, other materials are indeed as looked up as a sort of a replacement or a sort of a research problem in the laboratory. There are many issues with the third generation solar cells, apart from having a good part is flexibility. So the question is, will they ever come to market? How are we going to develop a technology out of these silicon solar cells? So this part I will skip. Actually, I lack of time. We have to really, when you are designing the material, one statement I can make it, you have to look at very close to the properties of the sunlight, which part of the spectrum you get the light, and how to design this material. So this is more like a design aspect. This is something, a spectrum of a solar radiation. You see that you get light the solar spectrum is indeed a you get light across the wavelength in the visible part, infrared part, and UV part. So it's a distribution of a wavelength. You get light. Some part of it's and then the photon flux is as a function of a wavelength. So you see that photon flux, you get very good photon flux in visible part of the spectrum. That's what matters for the solar cell applications. But you get a fraction of light in near IR as well as the visible part of the spectrum. We set it up one challenge in our lab. This is the example I will give, and then I will stop and then we can open up for the discussion. So there are challenges here. One of the grand challenge in the solar cell is how are we going to maximize the efficiency, and how are we going to deal with the loss mechanisms, and okay, how are we going to encounter the loss mechanism, how you limit the loss mechanism, and improve the efficiency. So here is the basic sort of a first key step in solar cells. You shine the light, incoming photon has an energy which matches with the band gap, you excite the electron. This electron has several pathways. Either, first of all, is very important in the solar cells, you separate this hole and electron, collect to the electrode and maximize the efficiency. But there are competitive processes. One of the competitive process is this is a excited state losses, which we call a basically anything which is above band gap, which is you emit, that is gone, that is you lose in the form of a heat. What you collect is only the Fermi energy, and that's the maximum voltage you can get from the solar cells. Look at this solar spectrum here. Here is the basic calculation. This is the way this is Shockley-Queisser limit or thermodynamic limit people call in the field. This is the theory paper they published in Journal Applied Physics in 1961, where they did this, all the loss mechanisms that they take into account, they did the calculations and they set up the limit. Look at here. This is the light which is not absorbed when you use silicon as a semiconductor. The high energy photons will lose a thermal in the form of heat. I showed you the animation. Thermalization losses is 33%. You put a metal contact on a semiconductor, there are defects at those interface, those are extraction losses, and total available limit for a band gap of a 1.41 EV is 33%. So you are basically losing almost more than 65 to 70% of the light without doing any work here. But within that window of a 33%, how are you going to maximize the efficiency? So this is the questions we ask, and we did first basically a sort of a beautiful piece of work where we did looked at how this bridge plays a role in the excited state. So we did this one by using a basically a femtosecond Raman here, because vibrations, these probes we use, and then excited state, in a organic we call it exciton. You shine the light, you create this Frenkel exciton, and this exciton we understood the preferred route is this red line. You create the polaron pair without this blue line, but it is very clear from the literature that it undergoes the manifold something called intramolecular charge transfer. So we wanted to see what is the role of this bridge. When we are growing a polymer chain, we have to make it sure that are we going to make it a very rigid chain? Are you going to make it, because these single bonds, when you bridge these kind of a thing, they are flexible, they do rotate. And then we wanted to see that what kind of geometry this polymer adopt when in the ground state, in the excited state, because it is indeed very, very important to understand the geometry of the polymer in the excited state. So we did look at basically using the FS, femtosecond stimulated Raman spectrum, and if I want to highlight these two, peaks here, we see that the width of these peaks changes, and indeed we have found that. So this is a very important fundamental research for providing a design principles. What we learned from this research is you need to have a very rigid backbone, because polymer indeed adopt a different geometry in the excited state to the ground state. Going forward in this similar area, we recently started about a concept called singlet exciton fission based solar cells. So let's take a silicon which takes away the low energy photon, and you coat a organic dye upon it. When you coat organic dye, you simply don't coat it. The dye has a specific property. It takes away the high energy photon, which is not doing the important work in case of silicon, because those high energy photon you lose in the form of thermal energy. We coat the dye upon it. Essentially, the dye, we have a property, something called undergoes singlet exciton fission. So there are calculations people have done it. This is what I have shown here, power conversion efficiency versus the band gap. The plot, you see that it's a band gap dependent. The blue part of the spectrum, you see that you get a, something around 1.4, you get efficiency close to 33%. But if you make it very low band gap material, you get a very low efficiency, and wide band gap, you also get a very high. If you use the concept which I'm proposing here, then if singlet diffusion based solar cells, you can really jack up the efficiency of more than 40%. So this is something very, very exciting for us. Then we started looking at, we proposed recently a molecular design strategies, because it is not easy to design the dye which undergoes singlet fission. So we learned whatever from our research, we wrote this perspective which for the community, how people should design molecular design strategies for the exciton fission here. But there are many fundamental questions in this area. Our interest is always looking at those fundamental questions and how the coupling between the chromophore, which plays a very, very important role for a molecule to undergo singlet fission. So here is a student from Krishna Priya. I'm very proud. She's coming from Kerala. So she's the one who put a bridge between two pentacene ladders. So this her, I'm not showing the synthesis here, but however, what she did is she put a three different type of a chromophore, for example, phenyl, thiophene, and selenophene. This is a pi-conjugated chromophore. And she looked upon how a electronic coupling between these two pentacene ladders plays a role to the dye undergoes singlet fission. Okay, so if you put a phenyl, there is indeed a poor coupling because of the torsional effect. If you put thiophene and selenophene, the material is very planar here. So this is the work which she published in last year, where she talks about like looking at the optical properties, where you see that indeed there is a simple absorption spectra of a dye shows there is indeed difference between electronic coupling. Here is a phenyl one, which has a very high oscillator strength, very high extinction coefficient, but it is blue shifted. When you put thiophene and selenophene, it's a red shifted. That indeed tells you there is a strong coupling when you put thiophene and selenophene, because the bridge is very planar, whereas when you put a phenyl as a linker, essentially you twist the phenyl and then you have a blue shifted spectra. Then I will not describe the ultra-fast dynamics, which is done in a collaborations with my friend in a TIFR Mumbai, where we saw here, interestingly, what we see when we did ultra-fast spectroscopy, phenyl undergoes singlet fission, we see triplet signatures, whereas thiophene and selenophene does not undergo singlet fission. So we did again a detailed studies and proved that there is no dimer. And there is no singlet fission in other two dimers. So these are all very detailed ultra-fast studies where we see a signature only in a phenyl dimer. And we confirm those triplet pairs are indeed triplet pairs by putting an oxygenated and deoxygenated solution. You can see that deoxygenated solution is long-lived triplets, and when you oxygenate, the triplets are getting quenched here. So there was an indeed challenge. How are we going to explain the mechanisms behind this research? Then we did a lot of computational studies, and we came up with the idea how the spin density localizations on the pentacene dimer plays an important role when you are localized spin density and delocalized spin density. So this is the more detailed computational studies here. So what is happening here is the present mechanism, whatever we propose, it does not essentially require this, basically the singlet state already has a partial TT character. That's one of the major outcome. And the bridge plays very, very important role, how the, how it contributes, in terms of, to facilitate the exchange of alpha and beta electron and the solvent polarity. And indeed, I did not touch upon it, but indeed it plays an important role. So with this one, I think if I have few minutes, I will talk this next part, but let me just thank people here. One of the collaborator here is Professor Das Gupta in TIFR Mumbai. And these are the students who have tirelessly work on these very, very challenging project. Funding comes from Swaran Jayanti and ISRO STC, Global Challenge Research Fund, and IISc Bangalore. I don't know how much time I have. Maybe organizers can tell me how much do I have? Few minutes?
You don't have.
Okay, fine. Then I will stop here. I will stop here, Pradeep.
Yeah,
Thank you.
We'll take some questions.
Okay, I'll take questions. Okay, thank you.
Professor Mujib is sharing this session.
Hello.
Yeah, please.
Thank you very much for your exciting talk about the exciting molecules and putting forward the novel ideas before us and setting aside this valuable time for us. Thank you. And we are now opening for discussion. Please, audience, please.
So Satish, let me start by asking that ultimately this is a whole thing is about thermodynamics.
Yeah.
So people would like to know how much actually can be saved from whatever way the energy losses are. Is there some kind of a limit that we have? Is there a limit that we can reach? Are there better limits with molecular materials? Are
Yes.
there better with silicon?
Yeah, okay. So I think I talked about this Shockley-Queisser limit, the thermodynamic limit, actually, because I was talking about this basically one of our idea I was proposing here, because this is the animation I was talking here. So you see that here is what has been plotted. I think I rushed upon here a little bit fast. I should have spent more time here. This is the solar spectrum, the red part. You see that silicon absorbs there at 1.1 eV. That is the majority of the work for the silicon is done in this part of the spectrum. But however, the blue part of the spectrum here is very high energy photon. They are all loss mechanisms. So you have to encounter these loss mechanisms by putting some organic dye. It is simple to do. You just take a silicon solar cells and you can coat a very thin layer of organic dye which only absorbs the blue part of the spectrum. It does not really, take away the other part of the spectrum. If you take away this blue part of the spectrum, high energy, wide band gap organic molecules coating on a silicon, it can boost the efficiency from a thermodynamic limit for the silicon is close to 30%, 1.1 EV here. You can go up to at least the calculation suggests that it can go up to 43%. So you can go beyond Shockley-Queisser limit, but you're not really complicating the device design. It's a very simple, a thin layer coating of an organic dye on a surface of a silicon, and you're boosting the efficiency from thermodynamically beyond thermodynamic limit. So that's the idea of using molecules in this work.
Do we have molecules that have sort of similar stability as silicon?
We know these molecules are, this is one of the, again, I will not mislead you, because the data is, in terms of stability data, people have not really done a very detailed stability studies. But if you look at the successful story of LEDs, in a display, if you have a proper encapsulation technologies on a surface, you can really make it, their LEDs are already in the market now. So based on molecules, there is a successful story already where products have already been demonstrated and people are using those products. So if you use similar encapsulation technologies here, and then if you make it, the organic solar cells are going to make a big impact. In addition to that, in room light, applications, there are some within the house. These are very efficient than silicon. For example, you are many flexible, you can decorate your house by using the light, in the room light, whatever you get it, because the extinction coefficient of this dye is very high. So simply you are in the night time, for example, you are turning on the light and that light will be absorbed by these curtains in your house or decorate a frame in a house, and that can give a very high efficiency where you cannot put silicon there actually. So that's another major applications which is coming out, in-house applications where, for example, people can integrate a glass buildings, major glasses. We can coat a simple thin layer of a organic dye on it. It does not carry any weight. Whereas it aesthetically, it looks very elegant, as well as you can harvest the sunlight during the daytime. So those are many building integrated photovoltaic applications is a massive way industry is evolving here actually.
Sir, I have one question. Thank you, sir, for your excellent presentation. So in some of your final slides, you have shown one pentacene molecule
Yeah.
And you have shown the femtosecond studies of those molecules.
Yes.
So did you apply those molecule for the bulk heterojunction or organic solar cells?
We have not applied for bulk heterojunction organic solar cells because the absorption here is indeed, it's good absorption. I think that's a good idea to apply for a bulk heterojunction solar cells. But bulk heterojunction solar cells, our work, which I did not touch upon because of the lack of time, we mainly do bulk heterojunction by using polymer because we want to make a printable ink. We want to print these solar cells for large applications. So that's the reason our interest is always in that's a separate research topic where we get very high efficiency now in IISc Bangalore. We get efficiency of 70 to 18% in our lab, where we use a polymer based system, because the idea is eventually the number is good, but you want to print those things. Okay, if you start printing, then it makes a big impact on a technology.
So did you find any relation between the excited dynamics of those molecules? You have shown there one phenyl ring is attached and thiophene, and so this pi linking is there any role in the excited state dynamics? If you are
It is
changing the
basically indeed, because if you look at now, this is what actually, if you look at here, this is the plot where you see that the black one, the kinetics we have extracted from ultra fast spectroscopy. You see the black one, which is showing a signature of a triplet here. If I see my cursor here,
yes.
Whereas the blue and the red one here is mostly thiophene and selenophene. They only generate singlets. They do not generate a triplet signature. So we see there is a big difference in excited state photophysics when you do we have phenyl bridge, a thiophene and selenophene.
Okay. Yeah. Thank you. Thank you.
Thank you.